All right, section 8.5 is on systems of linear equations. And so this is stuff you've seen. It was back in chapter 4. This section is basically a review of all of chapter 4. And let's just start off with a definition of what a system of linear equations is. And then we're going to go through a couple of examples, but if you want a more in-depth look at this, you can check out sections 4.1, 4.2, and 4.3. I have videos up on my YouTube channel. If you want to go to the Math 95 playlist, you should see them there. That'll give you a few more problems to work through. So a system of linear equations is just when you have two or more linear equations. So the solution for the system, besides a couple of special cases, which we'll see, is usually an ordered pair, because what we're basically looking at is where the two lines, two or more lines intersect. So we talked about 3 different methods for solving a system of linear equations back in chapter 4. And so we're going to look at all 3 of them in this section. We're going to look at the first one, which is graphing. And this one just kind of gives you a visual representation of what it means to solve a linear or a system of linear equations. But this one isn't the best because sometimes if the point isn't exactly on a whole number, you might have to estimate what that number is. So that one's not used most of the time, but it is good for understanding what we're doing. The second method we went through was substitution. And the third method is elimination. And sometimes you'll hear this one called the addition method if you're looking up some other sources for help on these. I'll call it elimination though, because what we're doing is eliminating one of the variables. In the second one, we're making a substitution. So they're pretty much just named based on what you're doing. So let's go ahead and take a look at some graphing examples first. And yeah, we'll go ahead and put the first one here. I have some room. And it's going to be a little bit trickier to see the solutions on the graph paper, so it's not going to be exact, but I'm going to do my best to make the graph as exact as possible. So we're told to solve by graphing, and on the homework, you will be given a specific method. If you're told to solve by graphing, if you're told to solve by substitution or elimination, a lot of the times they'll kind of pair those together. But for those ones they'll normally just have you put in the solution. With graphing, they might actually have you graph the 2 lines. So for this first one here, we're given x minus y equals 3 and 2x minus y equals 4. So first thing we want to do with these two is put them into a form that makes them a little bit easier to graph. So I'm going to go ahead and put both of these into slope-intercept form. So I'm going to take this x minus y equals 3, and I'm going to solve for y. So first thing I'll do is subtract over the x. So we get negative y equals, equals negative x, and then it's positive 3, so plus 3. Now I want this to be a positive y, so let's go ahead and divide every single term by a negative 1. So we get a positive y equals a positive x, and then 3 divided by negative 1 is negative 3. So we have our first equation here, and then we'll go ahead and do the same thing with our second equation, and then we'll go ahead and take a look at how to graph these two. So again, first thing I want to do is get this y by itself, so let's subtract the 2x from both sides. So we get negative y equals negative 2x plus 4. And then again, let's divide everything by a negative 1. So we get y equals negative 2 over negative 1 is positive 2x. and then a -4. That's our second equation. So I'm going to go ahead and set up the set of axes here, and then we'll talk about how to graph these. And again, I'm going to try to do this as nicely as possible so that we can see the exact solution. Let's go ahead and put in some tick marks. So let's do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, and 5. Okay, so let's go ahead and take a look at our two equations. Our first equation here, remember in y equals mx plus b, the number at the end is our y-intercept. So our y-intercept here is -3. And I'm actually going to rewrite this in the correct form. So our y-intercept is the point 0, -3. So let's put a point over here at -3. And now let's go ahead and plot another point using our slope. So our slope here is this number in front of the x, which you can't see, which means it's a 1. So our slope is 1 over 1. So this tells us to go up 1 and then right 1 because they're both positive. So remember, rise is on top, run is on the bottom. So positive for both means up and right. So we're going to go up 1 over 1, up 1 over 1. And I'm actually going to do a few points to try to get this as exact as possible. But if you noticed, based on kind of my tick marks not being exactly evenly spread out, my line might not be exactly through these points. These points might not be straight, but we're going to do our best and draw the line through those points. When you're solving these by graphing, it's best to do as many points as possible. So I did 4 there. It should hopefully be good. Now let's go ahead and I wonder if I can change the color. No, okay, we'll stick with this. Let's go ahead and look at our other line here now. So our y-intercept here, again, is the point at the end, the number at the end, so it's 0, -4. So we're going to start at -4 on the y-axis. And then our slope is 2, is this 2 in the front. So our slope, or m, is 2 over 1. Again, they're both positive, so we're going to go up to right 2. And notice how I'm not saying up to over, whoops, sorry, up to over to the right 1. Notice how I'm not saying up to over 1. I'm specifying that we're going to the right because sometimes if there were a negative on the bottom, we would go to the left. So it's all dependent on that sign. So let's go ahead and go up 2. So up 2 to the right 1, and we actually end up on the same point here. So I'm not going to, let me change the color here. So we started here and our second point was right here. So I'm not going to go ahead and put any more points here because we can actually see where they connect. Let me go ahead and put our line through these 2 points. Oh, nice, it actually showed up red. And I'm trying to get this as nicely as possible through those 2 points there. Now, if we go ahead and look at our 2 lines here, we're looking for the point of intersection, which is this point right here, which means our solution, because we went over to the right 1, and this is at -2, our solution for the system of equations is the point 1, -2. And this is what your actual solution is. So you want to make sure that you actually put the point as your solution. Just graphing it isn't enough. You have to say what that point is, or you could just say x equals 1, y equals -2. Those would both be correct, but usually we want to write it as an ordered pair. All right, let's go ahead and look at one more graphing problem, and then we'll take a look at some substitution. So number 2 here, we're given 2x plus y equals -5, and negative x plus 3y equals 6. So again, first thing I'm going to do is put these into slope-intercept form so that we can graph them. So let's take our 2x plus y equals -5 and solve for y. This one's pretty nice because our y doesn't have a coefficient. So all I have to do is subtract this 2x from both sides. We get y equals -2x minus 5 because it's negative. So here's one of our equations already. Now let's go ahead and do the same thing with our other one. So -x plus 3y equals 6. Let's add the x to both sides because it's negative this time. So we get 3y equals a positive x, so x plus 6 because it's also positive. Now we want to divide both sides by 3, and we want to divide every single term by 3, so I'm going to split it up like this. And so on the left, we're left with a y, and now this is the one to be careful with. So notice how we have x over 3. Now the way to think about this so that we can clearly see the slope is think about what number is in front of the x if you don't see one. There's always a 1 there. So now we can think of this as a 1/3 x because we've 1 over 3. So you're kind of pulling that x out to the right, plus 6 over 3 is 2. Now that we have our two equations in slope-intercept form, we can go ahead and graph this. So I'll set up our coordinate plane here. And let's put some tick marks on there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's go down 1, 2, whoops. 2, 3, 4, 5. This one is actually going to have to go down a little bit further, so we'll talk about y in a second. 1, 2, 3, 4, 5. All right, so now let's take a look at our two equations. We have a -2x minus 5. So our y-intercept here is 0, -5. And so if I go to 0, -5, that is all the way down at this point. So let me do this one in a different color. All the way down here. And if we look at our slope, we have a -2. So our slope is -2 over 1. So this is saying go down 2 and then right 1. You want to make sure that your line is going down because it's a negative slope. So if we go ahead and look at this, if I were to go down 2, we would need to go down 2 to the right 1. So we would have a point down there somewhere, which is kind of off our graph. So instead of going down 2 to the right 1, we can do the opposite and go up 2 to the left 1. So you're basically going to switch the sign so that that negative over here is on the bottom instead. So it's 2 over -1, which is up 2, left 1. So you can always move that negative. Just make sure you don't put it on the top and on the bottom. All right, now let's go ahead and just do one more point. So let's go up 2 to the left 1. And I'll do one more. So starting here, we go up 2 to the left 1. Trying to make those line up as best we can. The scaling is a little bit off, but we should be able to see our line pretty nicely through those points. It's just these two that are kind of off. Okay. All right, so now Let's go ahead and look at our other line. So our y-intercept for this line is 2. So we're going to have a y-intercept of 0, 2. And our slope is 1 over 3. That one's already a fraction, so we're just going to go up 1, right 3. Now, let's go ahead and plot our y-intercept. So we're going to be up at 2. And then our slope is up 1 to the right 3. So I'm going to go up 1 to the right 1, 2, 3. And now if I plot more points in this direction, it's going to get further and further away from this green line here that we want to see where they intersect. So instead of going up 1 to the right 3, I'm going to go down 1 to the left 1, 2, 3. And they line up really nicely at that point right there. My scale just looks a little off because of the way my tick marks were drawn. If you were doing this on graph paper, it would be a lot easier to see. But we can see that they line up really nicely at that point right there. So that means that our solution, is the point, so let's see, 1, 2, 3, so -3, comma 1. That is the solution for the system of equations. So that's graphing. That's pretty much visually what we're looking for, is the point where those two lines intersect. Now let's go ahead and look at some examples of substitution. So for substitution, let's go ahead and just jump into an example. We'll look at one that's a little bit nicer first. So for this one, we're given, let's go ahead and do 5x minus 3y equals -6, and x equals 2 minus y. Now, this is a nice one to use with substitution, because what we're looking for with substitution is to have one of our variables by itself on one side of the equation. Because we have that, what we're going to do is we're going to take the expression for x, so x is equal to 2 minus y, and we're going to substitute it into the x in the other equation. So now if we go ahead and do that, we're going to have 5. And now because it's 5 times x, we're going to have 5 times 2 minus y. And let's put this in parentheses. That's what we're substituting. And now we're going to bring over the rest of the equation. So we still have minus 3y equals -6. So we've made a substitution. Now we can go ahead and distribute and solve for y. So we're going to get 10 minus 5y minus 3y equals -6. Let's combine like terms. So we have 10 minus 8y equals -6. Subtract 10 from both sides. We get -8y equals -16. And divide both sides by -8. And we get y equals 2. I don't know if you can hear my dog barking in the background. He's sleeping. All right, so now that we have y is equal to 2. This is half of the solution, because remember, we're looking for the point where they intersect. We're looking for the x and the y coordinate. Once we have this, we can take this and plug it back into either one of our equations. I'm going to plug it into the second equation because the x is already by itself, and that's what we're looking for. So let's go ahead and do that up here. We're going to have x equals 2 minus y. So we're going to have x equals 2 minus y, which is 2. So 2 minus 2, which means x is equal to 0. That is the second part of our solution. You could box the x and the y just like this. I'm going to write it as an ordered pair. So our x is 0 and our y is 2. That is where these two lines would intersect if we were to graph them. If, let's say we're given some kind of system where the x or the y is not already by itself. Let's go ahead and look at one of those. So number 2 here, we're given 2x plus y equals 6, and negative x minus 4y equals negative 24. Now, this is one of those systems where we could use elimination or substitution, and we'll talk about how we could use elimination when we get to that one in a second. But in order to use substitution, we want either the x or the y to be by itself in one of the equations. Now, one of these variables is really nice to get by itself. You're going to look for a variable that doesn't have a coefficient. If it does have a coefficient, it would work, but you'd introduce some fractions and it can get kind of messy. So what I like to do is just pick one of these variables that is already by itself. Well, in the sense that it doesn't have a coefficient. Now, if I were to take this equation and solve for y, I'm just going to subtract 2x from both sides. So we get y equals, and now we're not graphing this, so it doesn't matter if you do negative 2x first or second. I'm going to just keep it first, just so you're always in the habit of putting it into slope-intercept form. So we have y equals negative 2x plus 6. This is our first equation. Now we can take this expression for y and plug it into y in our other equation. So let's go ahead and rewrite that. So we're going to have negative x minus 4 times our expression for y, which is negative 2x plus 6, equals negative 24. Make sure you always plug it into the other equation. If you plug it into the same equation that you started with, you'll just get a true statement. Okay, so now let's go ahead and distribute. So we have a negative 8x. Make sure you distribute a negative 4, so this becomes a positive 8x minus 24 equals negative 24. And now something special happens with this one. If we combine like terms, those x's actually cancel out because they're opposites. So we get negative 24 equals negative 24. Now, anytime this happens where you end up with a true statement at the end, this means that you have a dependent system of equations. Now, what this means is that we have the same line. So if we were to graph these would actually be the exact same line. They would lie right on top of each other. And so what this means is that we have infinitely many, or an infinite number of solutions. So infinitely many solutions. And so normally you would write this as your solution. On MyMathLab, what they're going to do is they're going to write the solution like this. They'll still have infinitely many solutions written there. And they'll also have this kind of weird looking solution set of points. And so it's going to have the set, so that's the curly brackets, of xy points, such that, so a vertical bar, then you're going to put the equation, one of your equations that you started with. Normally it'll be the one that's a little bit more simplified. So in this case, we're going to use the first equation, and we're just going to put 2x plus y equals 6. So that's just saying that every single point on this line is a solution to this system of equations because they're exactly the same. They intersect at an infinite number of points. So this is what it's going to look like on MyMathLab. All right, so that's substitution. Now let's go ahead and take a look at elimination, and we'll be done with chapter 8. And again, we're just going to look at some examples here. So we're told to solve by elimination. And number 1 here, let's start off with one that's pretty nice. Let's go ahead and do 3x minus y equals -7, and 2x plus y equals -3. Now, this is one where if we solved it by substitution, that's totally doable. We could solve for the y in the second equation here, and it wouldn't be too bad because that y doesn't have a coefficient. For elimination, what we're looking for is opposites. So what I mean by that is if we look at these y's right here, we have a -1 and a 1 as our coefficients. Those are opposites of each other, which means that we can eliminate those y's, because if you remember, if we add opposites together, we get 0. And so the reason why this method is also called addition is because if we were to go ahead and add these two equations together, we're going to do vertical addition, so you want everything to line up. 3x plus 2x is 5x. -y plus y, well, those are opposites, so those cancel. Bring down the equal sign, and -7 plus -3 is -10. Now we have this nice linear equation, and we're just going to go ahead and solve it for x. So let's divide both sides by 5, and we get x equals -2. Elimination, if it's set up nicely for elimination, can be really nice and fast. So let's go ahead and find y, because remember we need both parts. Now it doesn't matter which one you plug it back into. Normally I'll look for an equation that has smaller numbers, or in this case, I'm going to pick the one that has a positive y, because we're solving for y. So I'm going to go ahead and take 2x plus y equals -3. And we're going to plug x equals -2 in for x. So we're going to have 2 times -2 plus y equals -3. 2 times -2 is -4 plus y equals -3. Add 4 to both sides, and we get y equals 1. And again, I'm going to go ahead and write this as an ordered pair. So we get -2, 1. That one was set up really nicely for elimination. Now let's go ahead and look at one that isn't set up quite as nicely, and it's also going to be one of our special cases. Number 2 here, we're given 2x minus y equals 4, and -6x plus 3y equals 0. So this is one where if we wanted to, we could solve it by substitution. We would want to solve for maybe the y in the first equation here, because the coefficient is just a -1. So we would have to change the sign, but it wouldn't be too bad. But we're going to solve this by elimination. And so with elimination, what we're looking for is opposites. So we have two options here. If we look at the x's, we have a 2 and a -6. So what we could do, kind of think of this like a least common denominator. So if we're looking at 2 and 6, what is the least common multiple of 2 and 6? Well, we could change the 2 into a 6 by multiplying it by 3. If we look at the y's, we have a -1 and a 3. We could change a 1 into a 3 by multiplying it by 3. So you have two options. I'm going to go ahead and look at the x's. So if we go ahead and look at the x's, Remember that we want them to be the same number, but we also want them to be opposites. So because we have a -6 here, we want to change this 2 into a +6. And so in order to do that, let me actually do this in a different color. And fix what I just erased. Sorry, this is supposed to be a 4. Let's go ahead and multiply this first equation by 3, because 3 times 2 would give us 6. Now, one thing to keep in mind here is that you do have to multiply this entire equation by 3, even the right-hand side. So let's go ahead and do that, and I'm going to rewrite both of them over to the right. So 3 times 2x is 6x. 3 times -1 is -3y equals 3 times 4 is 12. Now, if I go ahead and just bring this other equation over, that way I have them lined up nicely. Let's go ahead and now look at what we have. So this is a special case because if you look at the x's and the y's, they're both opposites. That normally won't happen unless you have this special case, but we do have opposites. So let's go ahead and add these two equations. So if we look at our x's, 6x plus -6x, those cancel. Let me actually change this color. So those guys cancel. -3y plus 3y, those also cancel. But I don't want to just leave the left-hand side empty. What happens when we add opposites together? Well, we get 0. And now on the right-hand side, 12 plus 0 is 12. Now we get this false statement. We get 0 equals 12, which is not true. Anytime you end up with something that is not true, this means that we have no solution. And so you might see it written as no solution. MyMathLab also likes to put the empty set because our solution set is empty. And our system of equations is called inconsistent. Inconsistent just means a system of equations with no solution. So again, that system of equations, those are the 3 methods for solving them. Just kind of a quick review since we saw that last class in Math 95. So if you want a longer review, check out sections 4.1, 4.2, and 4.3. 4.1 is graphing. 4.2 is substitution. And 4.3 is elimination. So if you want any more practice problems, you can take a look at those. We'll also do more of these in our Zoom session. But we're done with chapter 8. So now we'll be moving on to chapter 9. And this stuff is a little bit of what you've seen before, but it's going to be a lot of new stuff, but it's not too bad. And it's a really short chapter before we get to our long chapter 10.